Welcome to Uncle Fish. Today we're going to talk about part one, basically, of Programming Foundations, where the topic is binary. So, in order to understand binary, it's really important to just look at a computer system at its most basic level, right? And at its most basic level, it's an electrical system that has two states. Either the system is on or the system is off. It's an electrical system, so either there's current running through it or there's not current running through it, right? Um, so these two particular states, we need to somehow use these two states to convey information, exchange some information. Imagine that this is me trying to convey information to you, and we, basically have a light switch or something, right? So I may flick the switch on 3 times, and maybe that means something, right? Turn it on, off, whatever, some kind of a pattern, and then use that to convey some information to you. So something similar is happening here with binary as well. So let's give it some values here. So let's say on is 1, and let's say off is 0, right? So, okay, very good. Now, in order to take this information, these different states, maybe we have to combine these things together to, convey a bigger value or something else, right? So let's say, for example, that we wanted to use these particular states to convey numbers somehow, right? And maybe then use those particular things to convey like characters. We can make words out of it, right? And so on. So you get the idea. And I hope you're thinking like at its most basic state, if this is true, how do we get to things like recording this video and your laptop and all the programs that might use on your on a daily basis, right? So hopefully this will give you the understanding of those concepts as well. So using this, right, we want to see how are we going to take these particular states of a system and convert them to these things. So before we go down that path, it's really important to look at how we convey numbers in as humans, how we in our daily lives, right? So what we use is something very similar to this. We have, instead of 2 states, we have 10 states, right? So uh, okay, so what are our 10 numbers basically, right? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. 10 possible values basically that we can use. Okay, great. So we'll call this base 10. All right, so now in order to convey um, numbers using these things or bigger numbers, we combine these numbers in different places and they convey larger numbers, right? In the way back days, for example, you may literally write like tick marks. It would take a long time to convey, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to convey really big numbers. So this was a way to help give a more concise and simple way to communicate values to people, right? So let's look at this. How do we do this? So we'll take the very first spot of a number and we will assign something that says this is base 10, there's 10 states, and this is the 0th location, right? And you'll see why we start with 0. And you'll see this is kind of a foundational thing in computer science. So 10 to the power of 0 is equal to 1. Anything to the power of 0 equals to 1. So if I put a number 4 here, really what we're saying is it's 4 times 10 to the power of 0. So 4 times 10 to the power of 0, which we just said was 1, 4 equals 4. So any number that you put in here, basically times 1 equals that number. And so for the very first digit, it's pretty easy. You can convey a 0, a 1, a 2, a 3, 4, all the way to 9. Okay, that's great for single digit numbers, but we want to convey bigger numbers. So what if we have a second space here? And now it's no longer 10 to the power of 0, but 10 to the power of 1. If you follow that same format, 10 to the power of 1 is 10, right? So 10, and let's give any number here. Let's say we want to represent, I don't know, 34 or something. So 10 to the power of 1 is 10 times 3 is equal to 30, right? So any number in this position times this is going to give you that value, right? So this is 30 plus, and we already did 4, and that gives you the number 34. And we can carry this on, right? Let's go to the next top. So the next one, if you think about it, should be, we're counting here. So 0, 1, 10 to the 1, 10 to the 2. Well, 10 to the 2 is 100. So any number that you put here, it's 7 times 100. 700 plus the 30 plus the 4, 734. You can see how this is working, right? So 10 to the power of 3 is going to give you 1,000. 10 to the power of 4 is going to give you 10,000. And any value that you put in here, we can then, right? So this is 10 to the power of 4 is 10,000 times 2 is 20,000, right? So this is 20,000. And then, look, I don't know, I'm picking random numbers here, but 10 to the power of 3 is 1,000. 1,000 times 8 is 8,000. And if you add all these up, you get this big number. So hopefully that makes sense, and you can carry this on and really represent massive numbers. And this is what we do in our day-to-day life, how we communicate, right, with numbers. So let's do that same thing for binary and see if we can, again, use these two particular states. And I'm calling it binary because there's two states, right? So I should have kind of said that earlier, but this is binary, right? So let's use the same approach here. I'm going to clean this up. Give us some space. All right. So now we have in the very first space, it's base 2 now, not base 10, right? So you're going to say it's 2 to the power of 0. Well, what's 2 to the power of 0? Anything to the power of 0 is equal to 1, right? Okay, great. And then the next spot is going to be 2 to the power of 1. And then the next spot, 2 to the power of 2, and 2 to the power of 3, and so on. We'll go all the way up to 2 to the power of 5, and 6, and 7. And I'm stopping here for a reason, because these spaces here, there's 8 of them. This 1 or a 0 is called a bit. 8 of these together is called a byte. So I'm stopping there for a reason. And for good trivia, I think there was another a value here called a nibble as well. But anyway, so in this single byte, we're going to go see just what we can represent in binary. And remember, there's two possible states here. So let's do a really, really simple case of setting this to 1, right? What are we really saying here? What we're really saying here is 2 to the power of 0 is 1. 1 times 1 is 1. So that's your 1 value. If you put a 1 here as well, it would be 2 to the power of 1 is 2, times 1 is 2, right? We have 2 plus 1. This is a binary representation of the number 3. Okay? Let's say we want to set this to 0. If you set this particular number to 0, it would be 2 to the power of 2 is 4. But anything times 0 is 0, right? So you're not going to add it, it's just going to be 0. So if you think of that now, right, and treat these kind of like on-offs again, anytime there's a 1, you're saying count it. This is on. Anytime it's a 0, you're saying don't count it. This is off. Okay? So this would be 0 plus that. Okay? And let's say I set this to 1. So 2 to the power of 3 is 8. 8 times 1 is 8, so it's on. You would add. So 8 plus the 3 we already had is 11, right? So now 1011 is equal to 11 in integers, right? Hopefully that makes sense. And again, you can carry this on. So let's look at what this would be if we turned everything on. By everything on, I mean we set every bit to on. If you turn every bit to on, you get rid of this guy here, right? And say he's on as well. What you end up getting is 128 plus, that's 2 to the 7 is 128. 2 to the 6 is 64, plus 32, that's 2 to the 5, plus 16, that's 2 to the 4, right? Plus 8, we already did that one, plus 4, we already did that one, plus 2, and plus 1, right? And this equals to 255, okay? And if you set everyone to 0, you get 0, right? So there means that all of this being on and all of them being off actually gives you 256 possible values, okay? In an 8-bit system. Again, if you have more bits, then great, you can probably do more things because the next bit would be 2 to the 8th and 2 to the ninth, just like in our own counting. So, okay, this is good. We now know how we can, represent numbers. We kind of got to this stage. That's good. Um, but how did we know, right? Like when you think about it from an electrical perspective, how do you know when something is on? How do you know when something is off, right? I gave you the light switch example, but inside of your computer, it's not light that's going back and forth. So how do you know that, right? So this is where something known as transistors and microtransistors and come into play. This is what allows for us to know an electrical component when something is on, or a current is coming, or the current is not coming. So we're not going to go into these kinds of details. If you're interested in that, you should look into electrical engineering or computer engineering, right? There's a whole slew of complexity that is happening there in the physics of all this. We're not going to get into that, but this is again to just try to at least convey to you how we are trying to turn very basic states into information, right? So what we got to is this 256 values, right? Numbers that we can convey. But what good is that going to do? How do we convert that to characters? So a group got together, the American Standards Code for Information Interchange, and they did exactly that. They came up with a table that said there are, that the letter A, and I'm not going to give you the exact value, but the letter A equals to some number. Actually, I know this particular one. So the letter capital H equals to 72, right? The letter capital E equals to 69. Okay, so there's 256 of these types of characters that we can now represent with these numbers if you know those codes. And so computer systems were then programmed to do that conversion, right? So when you see the 72, they knew that that was an H, and now you can represent characters. Awesome. So hopefully that makes sense. Let's take one of these numbers and actually see how we could represent this. So let's take the H, for example, the 72. How would we represent this in binary, right? All right. So in order to represent 72, I guess everybody has their own way of doing it, but I like to go from the left to the right. So I have my spaces here, right? 8-bit system, taking this guy out here. Okay. All right. So I remember we said that the representation of this was 128. Well, 128 is bigger than 72. So I know I'm going to set that off, right? I don't want 128. 64 is less than. So I'm going to count that. So I'm going to put that in and say, I want 64. Now 64, which again, remember 64 is 2 to the power of 6. 2 to the power of 5 was 32. 64 plus 32, that's bigger than 72. So I definitely don't want that. I'm going to turn that off. 64 plus, so let's just do it here. So plus 0, right? Do I want 64 plus 2 to the power of 4, which is 16? That also is going to be too big of a number, so I don't want that either, right? 64 plus 8, that is 72. So I want that. So I'm going to set that to on. Sorry, I forgot to set that to off. I'm going to set that to on, so that's 8. And then I don't need the rest, so I'm going to set the rest to off, right? So this number now in binary, right, is equal to 64 plus 8 is equal to 72. So 0, 1, 0, 0, 1, 0, 0. 0 is equal to 72, which is equal to the letter H, right? So imagine now if you're in a computer system, this is how many bits it took me to just convey to you one letter. If I wanted to convey to you just the word hello, right, I would have to have a stream of 6 of these streams of 8 bits or 8 bytes, right, to convey to you this particular word, hello. Okay, so we're gonna get to the next level, and by the way, it doesn't stop at just binary. There's something called hexadecimal that's also used in computers, and hexadecimal gives you even bigger numbers. There's 16 possible states, 16 possible values, right? So we're not going to get too much into those details. We can cover that later, but hopefully this helps in at least trying to get you an understanding of what binary is and how binary is used inside of a computer. And I really want you to think through about, well, okay, how do I now take this information? Like, how does that become a programming language, right? How do I execute a program out of this? And we'll cover that in the next section. Thanks.